So in this tutorial we're going to look at ansi machining in Creo, and ansi machining stands for numeric or numerical control machining, and in a nutshell you'll create a product, or in this case a mold. You'll start with a solid block of metal, and then you'll mill away at that. So you'll mill some of that material away, and you'll end up with your finished part, which should look like your reference model that you've modelled in Creo. So the first thing that you need to do is open up your mold model. So we'll just open up an example here. So here's a mold model that I've created, which is a cavity that would make a Nissan badge. So you can see we've got drafts on this, we've got some rounds, and one of the first things that you're going to want to do is put a coordinate system on this, because by default the mold halves that the molding application makes don't have coordinate systems on them, and it's really useful to have a coordinate system when you're machining on the reference part, so that you can reference it as a 0 point or a home point on the milling machine. The milling machine calculates the distances to all of the points from that coordinate system. So if you select coordinate system here, and for these purposes we're going to put it on this corner of the part. So generally, if you're looking into the milling machine, so you're the operator of the milling machine, if you're looking in through the access doors, it's often good practice to put your coordinate system at the back right of the workpiece. So we'll just set the direction of the axes of that. It knows that it's now locked onto this vertex here, but we still haven't set its orientation. So if you click on orientation, and then this first box allows you to define the x-axis. So if you click in the box there and click on this back edge, and you can see the x-axis is now lined up with that back edge, and the second box has become highlighted here, and it's asking us for a direction for the y-axis, and we're going to click this edge here. Now by default what it's done there is it's put all the positive x values to the right of the workpiece, but with the y values it's put the positive into the workpiece. So this stalk of the coordinate system here would be negative y values, and this stalk of the coordinate system here is positive y values. Now for our purposes for machining, it's good practice to have the x and y and z axes all being positive away from the workpiece. So we need to flip this y axis round, and you can just do that here. If you click on flip, there we go. The positive direction of all the axes is pointing away from the workpiece, so we're happy with that. So we can click on OK there, and we have our new coordinate system. So once you've done that, you may want to just do a save of that, just so you've got it saved in a state where it's got the coordinate system on. And once you've done that, if you go to New, Manufacturing, ansi Assembly, so that's relates to ansi machining, and if you want to give that a name, you can. I suggest that you do, so that you can easily reference it later on. And you click on OK, and what you get is a new empty assembly, and one of the first things that you need to do in this assembly is pull your reference model, which in our case is this mold half, pull that through into the assembly. So the easiest way to do that is just click on this icon here, the Assemble Reference Model option. and then because our model's already open in the background, we can click on In Session and we can find it in this list. So there we go, and click on OK. Now again, by default it's brought it in the wrong way around, but it's asking us how do you want to constrain this, and because we put that coordinate system in the corner, we can use that as one of our references. So what I did there was just open the placement drop down, click on Select Component Item, and you can see our new coordinate system should be around here somewhere. We'll just flip this thing over. That's the coordinate system that we created in the part. So if you select that, and then you want to lock that onto the assembly coordinate system, so that should be down here. There you go, that's highlighting ansi assembly default coordinate system. That's what that code there means. So what have we got there? We've got the axes pointing in the right direction. Yep. We've got the x-axis here, the y-axis there, and the z-axis there, and it's happy. It's saying fully constrained, so we can OK that. So there you go, we've got our reference model that we're going to use as our target, if you like. That's what our machined workpiece should look like. The next thing that we need to do is we need to create a workpiece model. Now in some circles this would be called your stock, because it's the piece of material, of stock material, that you're beginning with, that you'll then be machining into this finished state. So this is the reference model in Creo, and we're now going to create the workpiece. So we can do that easily here. If you click on Automatic Workpiece, and straight away what's been done there is a block of material has been superimposed over the top of our reference model, and currently it's exactly the same size as the limits of the reference model. So that's what these zeros mean. 0 here on the x-axis, 0 here on the y, 0 there on the z as well. Now what we can do, we can open up some of these options up here. One of the first things that you may want to do is switch this into millimeters, if that's your chosen coordinates, chosen unit system, and you can start setting the offsets of that workpiece. So we could start off with a piece of stock that's longer than our finished model. You can see there I'm dynamically dragging that, and as I dynamically drag that, one of the figures here is changing, so it's in the y positive direction that I'm changing it. You can do y negative here as well, so we can have an offset there. We can have an offset in x negative, x positive. So all this is it's representing the piece of metal that you're beginning with at the start of your machining operation. So it's a block of these dimensions. Now for this exercise, we're going to set the offsets back to 0. So all these offsets need to be returned to 0, because the block that we're going to use is the same size as the outside of our mould. So we're happy with that, that's okay. What's happened here, you can see that this that was a cavity is now shaded green, and what that represents, if you just click on the reference workpiece here, right click and hide, you can see that we have two models, one inside the other. So this is the workpiece model, which is still shown here, and if we unhide this and hide the workpiece, we have the reference model still there. So they occupy the same space currently. So the next step that we're going to take is we're going to input some information about the milling machine that we're going to use to perform all the milling operations. And the way to do that is to open the Steps menu and click on Operation. And while we're in here, it's probably a good idea to set the 0 point of the machine. So as I said earlier, this is the point that the machine calculates all the distances to any other point from. So to define that, you click on this little arrow here, and it's asking you to select a coordinate system. We'll select the assembly coordinate system there, which is at the back right of our block. So it's happy with that. One of the next things that you're going to want to set is the retract surface. So this is the surface that when a tool has finished machining down in the cavity here, that it rises up to clear the rest of the part, or to clear any clamps that you've had to attach to this piece to hold it down in the machine. So if you click on the gather arrow at the side there, and by default it references your 0 point, so it's referencing the coordinate system that we set as our 0 point. And what it allows you to do is enter a value, or just drag this handle here up to a level above your part. So you set in this as a point that your tool will retract upwards to, a surface that your tool will retract up to clear any geometry inside the machine. So we've just dragged that up to a reasonable level. If we OK that, and then, as I said, we want to define some parameters about the machine that we're going to use. So if you click on this little icon here at the side of the ansi machine box, and as it says here, open machine tool dialog to create or redefine a machine. So we'll click on that. So by default it's called machine 1. You may want to rename it. It may be good for your projects to search online for a specific machine from a specific manufacturer, and then you can put real data in here, and you can put the actual name of the machine, say a Herco or a Haas or a Mazak. We'll just leave it as the default for the time being. The machine will be a mill, because these are all milling operations that we're going to perform on this part, and a 3-axis machine is fine for this job. Some of the other options that you may want to set, spindle maximum speed I think we'll set as 10,000. Horsepower you can set as well, and there's lots of options in there. You can really tie down the capabilities of the machine, but for the moment we'll just leave it at that. So if you click on OK and then OK again. So we've got everything set up now, and what we can start to do is define some machining operations to actually remove some material from this part. So probably the easiest way to get this material out of this cavity here is to use something in the software known as mill window. So that's this icon here, and now if you click on this, what mill window does is it allows you to view the part from above, so you're viewing it from the direction that the milling machine will approach it from, and then sketch boundary curves, and anything within that boundary that the machine can see, any surface that's contained within that boundary, it machines the surface. So it's probably easier to show you this. So if you click on placement, it's asking you for a plane, and we're just going to use this top surface of the mould. So if we click on that, and automatically it's picked up all the loops that you can detect from that angle. So it's picked up this outside loop, so that defines the edge of our part, so it's a square. It's picked up this circular loop here. You can see all the loops are represented by red lines. It's picked up this what we refer to as an island here, and it's picked up a matching one at the bottom here. So what that means is it won't try and machine these top surfaces. So this surface here, this island here, and this island here won't be touched, but everything that's not in there it will attempt to machine as best it can with the tools that we give it. So that's OK. So if we click on OK there, we've got a mill window defined now. And what we can do next with that mill window is we can we can use it to get rid of the majority of the material in this indentation. So if we go, let's go volume rough. So this volume rough operation is an ansi sequence which references the mill window that we've just created. And the other things that we need to define about this sequence are what sort of tool we're going to use, how are we going to drive that tool, so this is the parameters option, so that's to do with how quickly we're going to move the tool through the material, and then we have to define what milling window we want to use, so we will obviously be using the one that we've just defined. Now you can see there's lots of other options in there, but those are the sort of bare minimum that you need in order to define a sequence. Now if we click on Done, the first dialog that comes up is the tool creation dialog. Now we're going to have to create the tools for this job on the fly because we don't have a library of tools currently saved. So this first operation is a roughing operation, which means we're looking to take out the material as quickly as possible, and we're not too worried about the fine detail. So because of that, we'll probably use quite a large diameter cutter. So something like a 20mm diameter is quite large. And because we've got curved surfaces in this part, as you probably will have in your part, so these surfaces in here are curved, it's probably better to use a milling cutter that has a curved end on it rather than a flat end like the one that we're looking at in the dialog. So you can change that. That's known as an end mill, a one with a flat end. You can also set it to a ball mill, so you can see a ball mill has a hemisphere on the end of the mill. So we'll just set that back to 20mm. One of the other things that you can do in this dialog is get a quick preview of what the cross-section of your cutter looks like. So we can see ours here, it's 100mm long, it's 20mm in diameter, it's got a ball end to it, so it's a ball mill. And that's fine for our purposes. There are a lot of other dimensions and parameters that you can set in here, such as when a cutter reaches a certain point, sometimes it has a shoulder that either gets wider, so it goes up to a bigger diameter than the cutting section, or sometimes it drops down to a smaller diameter. So you can set all those parameters in here, which is probably a good idea for your project if you do a little bit of research into what cutters are available and what cutters are suitable for the material that you select for your mould. One last thing that you might want to do, you can give it a name. So at the moment, because it's set in settings here as tool number 1, it's the first tool that we created, by default it just gets T0001. If you want to give it a more descriptive name, that might be a good thing. So we could say 20mm ball mill. And then if you just click on apply, you can see that gets saved in tool position number 1. So let's just select that, and the next dialog that pops up is the parameters dialog. So it's asking you to set things like feeds and speeds and stepovers for the machining operation. So the first one that we come to is cut feed. So this is the feed rate, or the speed that the cutter will be forced through the material. So this tends to be in X and Y. So the greater this value, the more stress the more stress the cutter will be under, the more stress the machine will be under. Probably the higher the temperature will be reached at the cutting tip. So this has quite large implications for tool life, efficiency of the cut that you're taking. So let's assume, just for this instance, that this isn't a final mould, it's a prototype mould, and as such we're not making it out of a hard tool steel. and we're making it out of aluminium. So for this size of cutter, a cut feed of say 1,000 should be fine. Now you'll have to justify the mold materials that you choose, and obviously the corresponding cutting parameters that you choose as well. But these are just generic values that we're putting in here. So obviously that's going to take a little bit of research on your part. So the next input that's required here is the step depth. Now, how these machining operations work is they tend to move to a certain level within a cavity that needs to be machined out, and they'll run backwards and forwards through that on that level, clearing out material. And then when they've done on that level, they'll step down a certain amount to another level and clear out material at that level as well. So what you're setting here is the distance between individual levels. So again, the bigger you make this distance, the harder time you're giving the tool, the harder task that you're giving it. So again, assuming this is aluminium, just as an example, a 6mm step down is reasonable for that size of tool. So the next one that we come to is step over. Now, step over is similar to step depth, except it's not in the z-axis, it's not on the downwards movement of the cutter, it's on how far it steps over between cutting passes. So the diagram here is showing a cutting head. This is what we're looking at, this yellow circle here, from above, and it's travelling along a cutting path here, and when it gets to the end of the cutting path, it moves over by a certain amount and then does a parallel cutting path. And what we're defining is how far this cutter steps over. So with a 20mm cutter, if you want 50% overlap on your cuts, then your step over will be 10, because that's half of 20mm. So let's put that in at 10. Now this clearance distance that's required here, this is the distance that you want the tool to come out to clear any part geometry between cutting passes. So we'll put ours in at just 10mm for this example. And the last one is spindle speed, and it seems we've set the machine with a maximum possible speed of 10,000. Let's just use the 10,000 for this example. Again, you're going to have to justify all these figures by doing a little bit of research and a little bit of reading, and by matching them to the mold material that you've chosen and making sure that's appropriate for the injection molding situation that you've been asked to simulate. So we'll click on OK there, and the next input that it requires, if you just read up here, is a mill window. So we can select that mill window that we've already produced in the feature tree there, and it's happy now. It's got all the inputs that it requires to generate that sequence. And what it might be nice to do now is just have a little preview of what that milling sequence will look like. So you can do that up here in this menu. If you play path, and the most simple preview that you can have is this screenplay option. So it'll take it a little while to calculate, and then what it's done is it's created a solid model of the cutting head here, and it's going to move that over the model as if it was doing the cutting. So we'll slow this down just so that we can see what it's doing, and then we'll press play. So you can see it's coming in, and we get a nice little trace of the tool path here. So it's removing material, so it's travelling around the cavity at a certain depth that we've specified as the step down. So let's speed that up just to see what it does overall. So you can see it's using a backwards and forwards sort of hatching pattern, and then it's going round and finishing this outside edge as best it can. So that's okay. We can close that. If you want a little bit more sort of visual and sophisticated preview, a little bit more realistic, you can use the ansi check. And what this does, if you click on that, is it sends all the data that's been generated about that cutting path to a third-party application. This is Vericut that it sends it through to. This is a third-party developer that licenses this software to PTC. And if you just look in the window here, what we've got is a preview of the stop block, so you can see that's just flat on the top. We have a preview of what the area that's going to be cut as well. And if we click on play here, we'll actually see the material being removed. So that's a reasonable approximation of what the part will look like when that roughing pass is finished. So let's assume that we're happy with that. We can quit out of Vericut, and for our purposes we'll just ignore all changes, because you can make changes in Vericut that feed back into the software. But that's okay for us. We're happy with that sequence, so we can click on done. And let's assume that we're going to do one roughing pass, which we've just defined, and then we're going to do one finish pass as well. Again, you'll have to justify the number of passes that you do. You can do multiple roughing passes, multiple finish passes using different sort of hatching techniques to get a finer finish. But again, this is just the bare sort of bones of how to get an NC sequence working. So let's use the same mill window, but let's insert a finishing pass. So you've got the option here, finishing. So what it wants to know, just as the bare minimum, is the parameters. So that'll be the cutting parameters and the window that you want to use. We'll also select tool, and we need to select exclude surfaces as well, because in a finish pass it will ignore any islands that you've selected in your mill window. So it'll try and finish this top surface as well as finishing down in the cavity. But with exclude surfaces selected, we can select these surfaces to be excluded from milling, so that we constrain it to just working down in the mould cavity where we want it. Now in a real moulding situation, you may want to finish this top surface, but you probably want to finish it with a different operation type, maybe a surface milling operation type or a profile mill. So you do that separately to the milling that we're going to be doing down in the cavity there. So if we click on done, and then you can see in here I've already created a second ball mill. Now because this is a finishing pass, and the quality of surface that you get from this pass needs to be better than the roughing pass, we've actually sized down to quite a small mill, 6mm diameter ball mill, instead of the 20 that we had before. So we'll select that, and we'll put in some parameters for this as well. So I think we'll have 1000 again. We'll make the step over quite fine this time, so again we're going to achieve a much finer finish. We'll set that at 2mm. We'll set the clearance distance again, and spindle speed. And then it's asking us to select the mill window that we're going to use. So we'll select the one that we've already defined, and then it's asking us to define the surfaces to exclude from finishing. So we'll just click on this top surface anywhere, and it automatically gets all the surfaces in line with that. So we can click on OK there. Now if we want to play the path, just to check that it is only machining down in the cavity and it's not trying to finish these top surfaces as well. So we'll have a screen play first. And again you can see this calculating up here. You've got a percentage that's increasing, and there we go. So if we just play that path, we can see that it's doing its machining, indicated by these red lines down in the cavity, and then the yellow lines are indicating where it's rising out of the cavity to access the next piece of geometry. So if you really want to, you can check that in VeryCut as well, but we'll assume that that's gone fine. So that's essentially it for the basics of machining. As I've said earlier, there's a lot more types of processes that you may want to experiment with. The help for them all is available in the help file in Creo, which is quite comprehensive. But that's the bare bones of how to get the machining sequences working, how to generate them, and a rough guide on how to take the material out of your cavity. As I say, you'll probably want to have either more than one roughing pass, and probably more than one finishing pass. You may want to run several finishing passes using different techniques. There are hatching techniques that you can select, or what's known as a contour technique, which follows the contour lines of the part round in a constant Z level. And then there are mixtures of the two, but you'll have to experiment with that and keep looking at the simulated output in VeryCut to justify that you've got a reasonable finish on your mould.